Hey, what's up guys? This is Yiming Wang. I'm going to show you my work for project 2. So here, give you a brief cast of the code. And here is my board. Let's first check it out whether it works. And so from switch 9 to switch 5, they represent M. And from switch 4 to switch 0, they represent Q. And here we go. So this is number 00101, and multiply, let's try 1 and here is the binary output, and here is the number. So it's 5 multiplied by 6, so it's 30, and the binary output is 11110. Okay. And then we try to get a negative number. And how about multiply positive 7 by negative 8? So here we go. So it's 1, 1, 1, and negative 8 is 11100. So here it comes. And it seems to be easy to multiply two numbers by the human brain, but actually it's not. So let's first recall what we do with the decimal multiplication. So what we do is to multiply the multiplier by the first bit of the multiplicand and write the result here on the first row. And then we multiply the multiplicand multiplier by the second bit of the multiplicand and write the result here, and we have to shift one bit ahead, so we have the 0 here, and add these two numbers. So let's try 448. So my way to realize the function of multiplier is to reproduce the procedure on paper. So we have to add these 5 numbers. It's the result of 11111 multiplied by 11111. So what do we do for the first step is to multiply the multiplier by the every bit of the multiplicand and write it to a new a new register thing. So this guy has 8-bit, so it's the first row of this thing, and all the way down to the fifth bit of multiplicand, and write it to PP4. So now we actually get these 5 numbers, and what we have to do is just to add them. The result would be P equals PP0 all the way down to PP4, and the sum of these things. And this is how I add these 5 numbers. The first step is to add PP1 and PP0, and we get a sum of these two numbers, and just to use an adder to realize its function, and then add this number to PP2, and add this and add the next sum to PP3 and PP4, and we will get our final result P. However, these ideas only work for the unsigned numbers. Then I try to find some ideas from the daily life. This is how we deal with the problem with multiply two signed numbers. So we can strictly find that the result is negative, right? No matter what. And the second result is positive. And the third result is also positive. And actually, we don't care about the number is negative or positive when we do the multiplication. We just multiply the absolute value of these two numbers, so we get 72, and we have a sign negative, so we have negative 72. So my idea to avoid the sign number in multiplication is to just multiply the absolute value of this of all the two's complement negative values. For example, we have negative negative 15 or negative 14. Um, uh, we only need to use use this number to div to divide 10010, and we get the absolute value of negative 14. And the sign of the result is the highest bit of M XOR highest bit of Q. So to this step, we've already got the result in binary form. But you also see that I got this resulting 7-segment display form. Let me introduce how can we realize this function. And here we have the binary result. And the first thing we need to do is to convert it to the BCD form, and then then we can represent the decimal number use the encoder to encode this 4-bit binary number to a 7-segment display signal. And I have to be honest that I don't really know how to convert the binary number to BCD form. So I searched online and I found some other guys way to do that. And, and here is the code. For the encoder, it's not really very hard. So here is a Verilog code for that. So we have the BCD numbers on the left, and they are the cases in the always block, and we want the display to be these new numbers. So now let's take a look at the Verilog code. So here are the crazy inputs and wires and outputs. Yeah. And the first two always block is in order to recognize whether the input numbers are negative or positive. So it's the first bit, whether the first bit is 1, it's a negative number, and we take back to its take back to get its magnitude, else it's itself. And then use a generate block and some gen vars to get, and then we comes to the generator block. So this block is in order to calculate every small bit of this PP. So here is the PPIJ equals MJ and QI, and we have that. And PS is in order to shift this shift every row of PP, and we get a PS. And then these 4 blocks are in order to add this 5 PS result. So it's these 4 blocks here. and then we have the result. And this convert is in order to convert the resulting binary form to the BCD form. And these are just three 7-segment displays. Here the last one is the sign bit. So if the result is negative, so we have the negative. So here are some other sub-modules that I use up here. So this is the REPL carry adder module I use. So it's the full adder module inside the REPL carry adder module. And here is the interesting display module to convert the BCD number to the 7-segment display. And here we have the convert module. So that's all.